Okay, so before we move to the next topic, I want to just review this AWS algorithm first, very quickly. Okay, and then we'll study about cascaded AWS, algorithm today. So this diagram is showing the overall process of AWS learning. So in the beginning, we have to prepare the sample images. Here, the sample means, positive and negative samples, because this is supervised learning, right? So in this example, the positive samples means the face images. Negative samples means the non-face background kind of images, okay? And we also have to prepare features. The features in this paper is using, highlight features, but maybe in your case you can try to use different features. But in this paper, highlight feature is the main feature, and to calculate the highlight feature fast, they're using integral image. Okay, so based on the given samples and highlight features, this starting in the beginning by normalizing the weight. So every sample has its own weight. So, and the weight initially is all the same and normalized, value. Okay. And from the weight samples and the features. So, in the beginning, we try to calculate all the features, apply all the features into every sample. So for every feature, we try to calculate the error, EJ. Okay, so you may remember how to calculate the EJ. So based on the EJ, per every feature, we try to select just one feature and reclassifier based on that feature. So that is becoming the winner of this first loop. Okay, so that is HT. So HT means, that is, it looks like the best reclassifier or best feature for now, based on the error, because it has the lowest error. And then based on the selected HT, now we know the error of HT, that is ET, right? So based on the ET, we apply the beta. The beta means ET over 1 minus ET, right? So the beta into the weights. So in this way, we can update the weights. Okay. So we are repeating this process many times, like 2000, the large T predefined number of iterations. So finally, out of 180,000, available features, we are selecting, just 2,000 good features based from this process. So then those, for example, just 2,000. It can be 1,000, 2,000. It depends on your choice. But so using the 2,000, for example, features, we can construct a strong classifier. So let me move to the other page. Okay, finally, so in this page, in 37 of page section 2, okay, so the final strong classifier HX can be constructed by combining the selected 2,000 features. Okay, so in this case, by the way, in front of HTX, we are applying multiplying alpha. So alpha is another variable that is that has this formula, right? So let me draw. Okay, log function of 1 over beta. So it is actually inverse proportional to error. So good reclassifier can have very high value. Yes. Yeah, bad reclassifier can have very low value. So it is playing the role of kind of, confidence, belief value for every weak classifier. So in this way, we can combine all the weak classifiers. That is becoming the final strong classifier from the Ada boost algorithm. Okay, so that is very brief, summary of Ada boost algorithm. Do you have any question before we go? Yes, alpha is not normalized to 1. So as you can see from this graph, right? So error is between 0 and 1, right? So then alpha can be negative, positive infinite and negative infinite, crossing 0.5. Okay, it can be negative. Sometimes it can be negative, sometimes positive, even very big value and very small value. Okay. So here the 0.5 means the middle value of, right, median value of error. So alpha can be negative when it is over, error is over 0.5. So negative alpha means kind of bad feature. Positive alpha means that kind of good feature. Okay. Okay. So let's go to the next step. So I uploaded this new slide, face detection 3, in the e-learning platform and content folder as well. Okay. So based on this AWS training, based on the strong classifier, now the final step of this paper, for face detection, is cascaded AWS algorithm. Okay. So now we are working on this paper again. So the same paper, Vera and Johns. Okay. So if you remember, the key ideas of this paper were 3. So first of all, it is using integral image. So this is a kind of new idea. So to calculate the highlight feature very fast. Okay, that is one contribution, main idea. And the second one is Ada boost. It's kind of modified version of Ada boost. So Ada boost algorithm is selecting good features. The last, contribution is, cascaded classification. Okay. So basically, the strong classifier was already constructed in the second step using the Ada boost algorithm. By the way, by calculating, 2,000 features for 2,000 weak classifier per every, calculation every time, it is very expensive calculation still. So it is making the process slower. So the main target of cascade classifier is to speed up the the classification step. So instead of using those whole 2,000 features and 2,000 weak classifiers, the cascaded classifier is trying to apply those 2,000 weak classifiers in a kind of cascaded way. So in a kind of hierarchical way. Okay. So let's see how it's working. Okay. So this is overall kind of this diagram in page 4 of face detection 3 is explaining the overall flow, right? So once the modified Ada boost procedure is done, then we can select small set of critical features. So here the small set means 2,000. It's still a big number, but relatively much smaller than 180,000, right? So in that sense, we can say it is small set of critical features. Okay, so this means 2,000. Okay, 2,000. The results of the strength classifier from Ada boost, and then based on these 2,000 selected features, we are doing cascaded classification. We are generating, in other words, cascaded classifier structure. Okay, so today we'll study how to do this test. Okay, so to understand the cascaded classification, first of all we have to understand this, scanning process for face detection or object detection. Okay, so this is very typical way, not just for this paper, but for many cases. When we want to detect any object in the image, the typical way is to scanning the windows. So here the window means a small rectangle. So from the left top corner of the picture, we apply small window. And then inside just the window, so the window means, very small region of the picture, the cropped region of the picture, in other words. Okay, so just for the window region, so like, this small rectangle, okay, we apply the algorithm. So whatever it is, it can be AWS classification or any decision-making kind of stuff. Okay, we try to determine if by processing this small region, we try to determine if this region, this rectangle, is face or not. So window means, in other words, can be regarded as a sub-region. Okay, sub-rectangle. So if this small rectangle is face, then we can say, oh, this area is face. So this is kind of detection, right? So finally, we will apply the final cascaded, AWS classifier into every this region, every this window. So that's why it is taking much time and expensive. Okay, because it's not applied to the whole image just one time. We have to do this cascaded, AWS classification per every window. So we have to determine, oh, is it face or not? Face or not? Face or not? Finally, all yes window regions are left to be a face. So in this sample picture, we have to leave just 9 window regions as face, and all others should be ignored, should be no. Okay, that is how the classification is working. So when we say classification, cascaded AWS classifier or classification, it means it is for every window, not the whole picture in this case. Okay, so this is general, detection process. So let's keep that in mind, because the main reason why we are trying to upgrade the efficiency and the speed of the classification is because of this, very tedious and long process. Okay. Okay. Oh, by the way, it is yes. So if we are using just, the strong classifier we have constructed after the AWS, training, right? Then if we apply the strong classifier just directly without cascaded classifier, then it means we have to calculate 2,000 features per every window, because every window has, different pixels, right? Different information. So we have to calculate the feature again and again and again. Okay, 2,000 times. So that's why it can be slower. Okay. Okay. So because of that kind of inefficient process, 2,000 features, calculating 2,000 features every window, so it will take a long time. So to avoid that kind of inefficient process, so this cascaded approach is proposed in this paper. So here the cascade. What is cascade? Cascade means like a kind of waterfall. Okay, step by step kind of stuff, kind of structure. So like this kind of small waterfall, okay? So the water is flowing in every stage. So one waterfall here, second one, third one, step by step. When the water flows from the top, okay, then it is going down and down and down. So in every stage, the water can be filtered. So in the final stage, we can see just, some, for example, rocks or leaves. They might have been, filtered out in previous, stages. Okay. So finally, we have some more, purer, kind of water without any leaf or rock kind of stuff. Okay. So this is the cascade structure. So instead of processing all the information at once, it is processing information step by step, so stage by stage in this case. So every small part of this waterfall from the top to bottom is called a stage. Okay, so cascade structure is composed of stages. So we have to construct the stages for the whole cascade classification. So that is the basic idea of cascade. Okay, is that clear? Okay, so let's see then how we can work, on this. Okay, so information is processed step by step. So more formally, stage by stage. Okay, so in every stage, we are trying to filter out some unnecessary information. Okay, so we can use this kind of diagram more formally. So this number 1, 2, 3, 4 represent every stage. Stage 1, stage 2, 3, 4. Okay. So in every stage, every stage is regarded as a kind of classifier. By the way, it is not just weak classifier, and it is not strong classifier. It is kind of intermediate level of classifier. It means instead of using all the 2,000 features or 2,000 reclassifiers, such as, the strong classifier, right? In case of strong, the basic concept of strong classifier is, it has to use all the reclassifiers, right? We have to integrate all of them. And then we can create the strong classifier. By the way, in every stage, it is composed of some partial set of strong classifier. So instead of 2,000, for example, in stage 1, you can use just 10 of them. In stage 2, you can use the other, 20 of them. Okay, in this way, so every stage is kind of partial, smaller subset of strong classifier. Okay, so in this way, instead of processing all 2,000 at once, we process the classification, partially, step by step, stage by stage. From one, the topmost one, the first one, number 1 stage, to the second stage, third stage, fourth stage. So, in other words, every stage is kind of classifier, even though it is not the final, the strong classifier, not weak classifier, but it is still a classifier. Okay, so every stage is also a combination of weak classifiers, but the much smaller number of combinations. Okay, instead of 2,000, it can be 10, 20, 50, 100, blah, blah, blah. Okay, that is every stage classifier. So I also can say, every stage is stage classifier. Okay, so in stage 1, so stage 1 can classify something, not perfect, not like strong, as strong as, strong classifier, right? But still it can do some classification. So after classification in stage 1, we can say yes or no, true or false. because, the classifier in this paper, for face detection, it is basically, binary classification, right? So it's face or not. So true means face. False means non-face. So stage 1 classifier classifies the input image as true or sometimes as false. Okay? So what it means in this diagram is, when stage 1 determines, classify the input as false, then it is false, rejected. Oh, it's not face. Okay? By the way, when stage 1 say true, oh, it looks like a face. Yes, exactly. In case of false, then we don't need to process anymore. Okay? And in case stage 1 say true, yes, then we have to process more with stage 2 in the next stage. So stage 2 tries to classify again. And stage 2 also can make the determination. Oh, it is not face. Then stop, it is false. But if stage 2 still say, oh, it is true, oh, it looks like face, then it goes to stage 3. Stage 3 also do the same thing. 4, the same thing. And finally, the last stage. Okay. So in this way, just true, yes answer, result can be processed as, processed to the next stage. So, yeah. Yes, exactly. Yeah. Okay. Yeah. Good question. So someone asked the question like, oh, in this case, yeah, we can increase the false positive rate because every stage is much weaker classifier than strong classifier, right? Not weak classifier itself, but weaker intermediate, right, level of classifier. So its false positive rate will be very large. Okay, that's why we are doing cascade. Okay, so from stage 1. So we don't know, we didn't study yet, how we construct the stage. Okay. By the way, we are designing every stage in this way. Like every stage can have a relatively large false positive rate, as you said, right? But true positive rate should be very high. For example, stage 1 is true positive rate is almost 99, more than 99%. So then, when stage 1 say true, okay, then we can believe the answer, right? Because the true positive rate is very high. By the way, relatively, false positive rate is not 0, right? It can be higher than strong classifier. So it means this answer T can be a very high level, can have many false positives, right? So that's why we are doing another stage classification too. So once 1 is done, then classifier 2 is trying to filter out more because the answer T can have more, false answers because of the false positive rate. Okay. Then to remove the false positive rate in every stage, so we have to design every stage with smaller false positive rate. So stage 1 has the biggest false positive rate. Stage 2 has a little bit smaller than that one. Stage 3 has smaller false positive rate. Stage 4, so the last one. The last one will have the minimum false positive rate. Is that clear? By the way, every stage has very high true positive rates, right? So when they say false, F, no, then it is more believable. You can be confident, right? So if stage 1 say, oh, it is not a phase, because of very high true positive rates, when stage 1 say no, it is not phase, then it means it is not phase. It is very high probability to be non-phase. Okay? Yeah, so we'll discuss more about the details later. Okay. So this way, so now we have, I think we have already discussed about this, false positive and true positive kind of stuff, right? So true positive means the phase is determined as phase. It means that the opposite is, true negative. Okay. For example, if true positive rate is 0.9, 90%, then true negative rate is becoming 0.1. So if we have very high true positive, then we have very small possibility of true negative. So somebody say, oh, phase, this is not a phase, right? Then there is the error rate of that answer is very small. Okay, 0.1. Actually, it is much smaller, 0.01 kind of stuff. Okay, that is true positive rate. False positive rate means, the first one is mistakenly classified as phase. Okay, that is false positive rate. So the final goal of the final classifier is, we have to achieve very high true positive rates, and we have to achieve very small false positive rates. That's the way to reduce the error, and the system is getting better, right? Detection is more accurate. Okay, so let's keep that in mind. And to design and construct every stage, we have to be careful, very careful about, true positive and false positive rates. Okay, so then let's start the structuring, of cascade structure. So in every stage, from stage 1, okay, so we prepare the samples, positive samples and negative samples in the same way. Okay, so in the first stage, as we have already discussed, the true positive rate, here I use the symbol D. Normally it is true positive rate is same as detection rate. We are using this term as well, detection rate. So, how many phases can be detected, right? The detection rate. So D, I use the symbol D. So in stage 1, for example, we are setting the D target false positive rate, detection rate, 99%. Very high number. Because it cannot be 100%, right? Because in reality, we have to allow some error. So instead of 100, 1.0, we are using 0.99, kind of high number. Or maybe you can use like 0.995 that way, okay? And then for false positive rate, we are starting with 0.5. It means 50%. So it is very big false positive rate number. Okay. So it means, from the whole samples, positive and negative samples. Here in this example, the positive samples are represented as red circles, red dots. And negative samples are represented as white dots. Okay. And if we input these all samples, positive and negative, then stage 1 will say yes for this, orange contoured area. So it means because of the high true positive rate, detection rates, most of the red positive samples will be classified as fake. Is that clear? Because so we are assuming we have very high detection rates, false positive rates. I'm sorry, true positive rates. Okay. By the way, the negative samples are supposed to be no, right? But the false positive rate is 50%. So among all the negative samples, half of them will be no, but the other half of them, in this example, the blue dots, okay, they are mistakenly classified as true, false, that is false positive rate. Half of them will be true, even though they are actually false. Okay, is that clear? So that is how stage 1 will be working with this rate, 99% of detection rate and 0.5%, 50% of false positive rate. Okay, so that should be the role of stage 1. So we will design stage 1 to have this kind of results, theoretically. Okay, we'll see how we can do that later. Okay. Anyways, this is the purpose of stage 1. 99% of true positive rate and 50% of false positive rate. Okay, so it is not good, right? It's not. It cannot be the final result. Okay, it just is the first step. Okay, so in the first step, we have to pass all the positive samples, and we have to filter out. In other words, 50 these white dots. Okay, these white dots. 50% of negative samples filter out. They will be filtered out, so they will have F results. Okay, so for example, when I input one region, one window, and stage 1 may filter out that window. This is not a face. Then that window is just not a face because of the high true positive rate. So we don't need to think anymore. That is not a face. By the way, if the window is classified as true face by stage 1, then it may have 50% of possibility to be a face, non-face, right? So because of 50% of false positive rate, so it can be it cannot be final decision. So it should be processed again in the second stage. So it is delivered to the transferred to the second stage. Okay, but just in case of no, false, they can be just filtered out. So here the filtered out means we don't need to process that window anymore. So some reasons, actually many reasons, many windows will be false, and they don't do any further stage classification. Yes, exactly. So our that in stage 2 we are scanning less samples, right? Yeah. So stage 2 is not processing all the sample or all the windows, right? Considering the scanning process. So in terms of stage 2, then it means stage 2 doesn't need to process all the. So stage 1 actually definitely should process all the window, right? Because all the windows should go to stage 1. But many of them will be filtered out in stage 1. So stage 2 does not need to process all of them. Stage 2 just process the filtered windows that was classified as true by stage 1. So we don't know the number, right? So it can be different for every picture. Okay? Yeah. So less input for stage 2. Then let's talk about stage 2. Then in that case, right, in stage 2, so now the target of stage 2 is, we are keeping the same detection rate. True positive rate, but we are decreasing the false positive rate to 25%, 0.25. That's half of the previous one, 50%, right? So in this way, okay, so all the red dots, the positive samples, should be preserved, okay, but some of them will be discarded, right? Inevitably, but all the positive samples, most of them, 99%, will be preserved. But in case of negative results from the previous 50%, now we can filter out half of them. So finally, it means until stage 2, 75% or 75% of negative samples will be filtered out, and just 25% will remain for the next stage. Okay. Then the true results, the filtered results that still include some negative samples, right? They will also pass to the transfer to the stage 3. So it means in stage 3 we will have less samples, less windows, just filtered out by stage 1 and stage 2. Okay, and many of them already filtered out by stage 2. So stage 3 will have much less number of samples, and it will also try to classify again. By the way, in stage 2, the detection rate, true positive rate, is also still 99%, 0.99. False positive rate is now half of the previous one, so it is becoming 0.125. So it means half of the previous one, so this part. Okay, so in this way, we can decrease the false positives in every stage. And stage 4, we have less false positive rate. Stage 5, less. 6, less. So in this way, in the final stage, we have the minimum false positive rate, and it can be the final filtering. Yes, exactly. Okay, so in every stage, like stage 2, 3, 4, 5, as we go down, 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 we will process less samples. In stage 1, again, it should process all the samples in the stage 1. But in stage 2, it will process much less number of samples. Stage 3, less than 2. Stage 4, less than 3. Okay? But every stage, they should do something more to filter out more negative samples. So in stage 1, we don't need to worry about the false positive too much, because the false positive rate is 50%. It is very high number, so it's very easy task. Okay, so we don't need to use many reclassifier. It doesn't need to be very strong classifier, right? So we can use just a few number of features in stage 1. In stage 2, we may need a little bit more. Stage 3, a little bit more. 4 more, and 5 more. Because they should be stronger, 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 stronger. So, but as we go down the stages, in the final stage, it should be maybe the strongest one, strongest, stage classifier, but they don't have many inputs. They will process just a few inputs. So even though the classifier is stronger, I mean, it means it is becoming heavier and slower, but they don't need to process all the samples, small number of samples. When we have to process all the samples at stage 1, we just use much weaker stage classifier with just a few number of reclassifiers. Make sense? So in this way, we can boost the speed, and we can make the process much efficient. So in other words, okay. What's your question? Question about scanning window approach. Scanning window smaller than the phase we are detecting. Yeah, just it depends on the size, but if it's too small, then it will be rejected. So there's a question. So when we are scanning in terms of the window, we also have to apply different size of windows. We are not just applying just one size because we don't know the size of the face before detection, right? So we have to apply all possible different sizes of rectangles. So it is a lot of rectangles in that way, a lot of windows. Okay, so it's not just about position. Okay, for one side we have to scan from the left top corner to right bottom. For the other side we have a window, we have to do that again. So how many different sides do you want to do, right? So that is also determining the accuracy of face detection, and it is also affecting the speed of the face detection. So that is kind of parameter, the factor. Okay, so whatever size of window, so this cascaded classifier structure is not concerning about that. It is just processing yes or no, just classify whatever size of window. Okay, yeah. So in other words, this process of stage-based approach, cascaded approach, we can say the role of every stage is filtering. Okay, so in stage 1, because we have high true positive rates, so true case, we are believing, we are assuming the true samples, true faces will be transferred to every stage, hopefully to the final stage. Okay, so true, or if the window was faced, then it will go to stage 1, and it will pass to stage 2, 3, 4, 5, and it will survive to the last one. So finally we can say, oh yes, this is phase. Okay, but in case of non-phase, background window, then they will hopefully be filtered out in some early stage. For example, in stage 1, half of them will be filtered out. In stage 2, half of them, the other half of them filtered out. Stage 3, half. Stage 4, half, in this way. So finally, anyways, we will not go deep down to the final stage. So they will be, hopefully, will be filtered out in the earlier stage. So finally, for non-phase windows, we are not processing a lot. We are processing all the stages just for real true phase windows. Is clear? So that's why this process, this cascaded one, is much faster than just simple strong classifier, just one classifier. Any question? So this is the basic, idea and structure of cascade structure. Okay. So now we will study more detail, then how, for every stage, then how can we design every stage in this way? Oh, this stage 1 should have 99% of true positive rate. Or this stage should have 50% of false positive rate. How can you do that? How can you make it working in this way? Okay, so we'll study about those steps from the next slide. Okay, so this is one example. Okay, so your question, the selection of weak classifier for each steps. Okay, then you mean how to select, right? Okay, so let's discuss from now. Okay, so in the beginning, from our previous AdaBoost training, we have selected 2,000 classifiers, good weak classifiers. They are good, right? They are selected, best 2,000 reclassifiers out of 180,000. Okay, they're good. But every single, classifier, F40, they are, as you know, every single reclassifier, F40 is one of them, the topmost one. So every single one is not enough for final classification, right? So that's still weak. But anyways, 2,000 reclassifiers has been selected from the previous AWS training. Okay. Then, if you remember, every reclassifier will have different alpha value. Okay. So we sorted the reclassifiers, selected 2,000 reclassifiers based on the alpha in descending order. Okay, so F40 in this example, just for example, will have the biggest alpha. Okay, F52 will have smaller than F40. F34 is next alpha. Okay, so in this way it is sorted, descending order. Okay, so it means among these 2,000 reclassifiers, F40 looks the best one. F52 looks the second one. F34 looks the third one. Okay. Yeah. Yes. F1, F40 has less error rates. Okay. Yeah. Then now from these selected and sorted reclassifiers, we can construct every stage. So for example, in stage 1, to achieve this goal of 99% of true positive rate and 50% of false positive rate, what we can do is we can just apply this F40. Okay, and then if F40 satisfy these two numbers, 99% of true positive rate and 50% of false positive rate, then it's done. So how can you know that? We can test this stage 1 classifier with all the samples we input. This is kind of learning process, right? So we input all the samples and we can calculate the detection rate and false positive rate. So if it is satisfying this number, so for example, if the detection rate is larger than 99% and false positive rate is less than or equal to 50%, 0.5, then it is satisfying the condition. Make sense? Hello? Everybody? Can you hear me? Hello? Can you hear me now? Oh, okay. So, sorry for the trouble. So I have kind of finishing it. Okay. So in this way, stage 2 can have more or other, weak classifiers, and it can achieve this rate, 99% of true positive rates and 25% of false positive rates. Okay. The reason why we have 3 weak classifiers. Why? Why do you think we need three weak classifiers? So this is just an example, okay? Why do you think we need more weak classifiers in stage 2? Very close. You said someone answered to maintain 99% of false positive. It is not. I mean, 99% should be the true positive rate. Okay, so it is more about false positive rate. Okay, to achieve less than 25% of false positive rate. Okay, so yeah, so keeping the true positive rate 99% and to achieve, no problem. Good answer. Yeah, okay. And to achieve the less false positive rate, we need, more reclassifiers because it should be more stronger, right? So normally we need it's not always. Sometimes some later stage classifiers may have similar number of reclassify from the previous one, but normally it has more reclassifiers to be stronger. Okay, yeah. So that's how stage 3 also will try to add more reclassifiers to satisfy this number, 12.5% of false positive. Okay, so that is the general concept of cascade structure. So we will construct the cascade structure in this way from stage 1 to the last one. Okay. Okay, so I think it's time for break. Let's have a 10-minute break now. And any other question? Okay, so let's have 10-minute break and we'll continue. So the details about constructing every stage. Thank you. We'll see you in 10 minutes. Okay. Thank you. Okay. So okay, I'm now going to page 12. Okay. So let's discuss more in detail about the every stage. Okay. So as we have already discussed, we have the ordered list of features, 2000 features. Okay, so they are ordered by alpha. Okay, so the top one, the first one, descending order, the first one is the best one in terms of alpha, biggest alpha with biggest alpha. Okay, so in stage 1, then we add from the top one as a kind of queue. Okay, so F40 is added to stage 1. Okay, and the target detection rate of stage 1 was 99%, and target false positive rate is 0.5%. When we added, F40, then we apply. So this, in this next slide, 13. So HX here, the HX is not the final, the strong classifier with 2000. Okay, so we got every stage is a kind of, intermediate level, kind of strong classifier, but not the real strong classifier. Okay, so it can have multiple weak classifiers. So the one stage classifier, it can be regarded as one, classifier with combination of, multiple weak classifiers. So in that sense, we can use the same formula, right? So alpha weighted sum of the selected weak classifiers can be used to make some decision based on some thresholds. Okay, so we'll discuss about the threshold later. Okay, anyways, so stage 1, even though we have just one weak classifier F40, we apply the formula. So it means we multiply alpha, the confidence value, to this weak classifier and try to make some decision classification. Okay, so to determine if this stage 1, the current stage 1 with just one weak classifier F40, if it is satisfying this 99% detection rate and 50% of false positive rate, the first step, once it is constructed, right, we apply stage 1 classifier to all the samples. Okay, and we can calculate rate D, detection rate, and false positive rate. And then we can check, if D and F satisfy. Here the satisfy means, the detection rate should be larger than or equal to 99%. That means 99%. It should be larger, right? If it is larger than 99%, for example, it is 99.5%. It's good, not bad. It doesn't need to be exactly 99%. But it is 98%, then it is not satisfying this rate. So bigger number is okay, right? In case of detection rate, bigger is better. So if stage 1 has, it's already 99.5%, it's good. Okay. In terms of, false positive rate, by the way, false positive rate, it should be less than or equal to 50%. It should be less or equal to 50, right? It should not be larger than 50. Because, when we say, false positive rate should be 50%, that's the maximum allowed, false positive rate. Okay? So in this way, we check if detection rate and false positive rate satisfy these, target numbers. Then we can just finish. It's done. Stage 1 is done. It is working good enough for stage 1. Okay. But if it doesn't satisfy this number, for example, if detection rate is less than 99 or the false positive rate is larger than 0.5, then it means we need more weak classifier. So we have to add one more weak classifier from the list. Okay. So for now, let's just assume, for F40 was enough for 99% of detection rate and 50% of false positive rate. Then we can just stop here. The stage 1 is now constructed. Okay. Yeah. Then let's go to stage 2. Okay, so stage 1 is now done. Now we are moving to stage 2. So the rates, so the true positive rate is 99% in stage 2. And the false positive rate is smaller than stage 1. So it will be, for example, like 12.5%. I'm sorry, 25%. Okay. Then we are starting from F52. We try to add the next one because F40 was used by stage 1. So we are starting with F52. We are adding F52 first. And then we try to apply all the same steps from number 2 to 5. Okay, so apply all the samples and calculate D and F, and if D and F satisfy, then finish with F52. But it doesn't satisfy the number, then we have to add more. So in case of stage 2, because the force particle rate is a little bit smaller, much smaller than the first stage 1, then we may need more features. So it doesn't satisfy. So we repeat again by adding one more feature. So we added the reclassifier 34. So now stage 2 has 2 reclassifiers. And then we follow the steps again. Okay, and we are checking if these 2 reclassifiers can satisfy the 25%, especially, the 25% of force particle rate. If it doesn't satisfy, then we have to add more. If it satisfies, then we can stop, right? Okay, so it didn't satisfy, so we are going to add one more. Okay, so we added one more reclassifier, F99 here. Okay, so now stage 2 has all 3 reclassifiers. So it finally satisfies the force particle rate, 25%. Then stage 2 is done. Okay, so again, so this stage 2, every time we add reclassifier 1, 2, 3, F52, 34, 99, okay, we apply this formula, strong classifier, even though again, even though it is not the real strong classifier, okay, but it is still a combination of reclassifiers, right? So we can use the same formula. So alpha weighted reclassifiers, some of them. Okay, so yeah, so this alpha weighted sum of these 3 reclassifiers can be applied to all the samples, right? And then it can give us this number. The force particle rate may be not exactly 25%. It can be 25 or 24, anyways, less than 25. Then we can stop here, the stage 2. So your question is, every stage, yeah, first of all, particle rate will decrease, right? Okay, for example, stage 1 was 50, 0.5, stage 2, 0.25. Okay, so we are intentionally, decreasing the force particle rate half of the previous one. The rate can be different in terms of implementation, but anyways, we are intentionally decreasing the targets. So here, 0.5, 0.25 is just target force particle rate, not the real one. The real one can be a little bit different, less than this number. Okay, so this is a target. When we are repeating this process, I mean between number 2 to 5, right? So we have to check that we need the target force particle rate. So we can check, and then at step 4, if the D and F satisfy, right? So here D and F satisfy. The satisfied number should be 0.25 for F. Okay, so we are intentionally decreasing the target numbers in this way. Okay, so the process continues from yeah. So another question from Panagan T. So if it doesn't satisfy the target value, then we have to add more. So we are repeating this process until it satisfies this number. So in this sense, stage 2 can have 3 features, 3 reclassifiers, or sometimes it can have 10 reclassifiers. Sometimes it can have 15. It depends on the samples and depends on the features. Yeah, so by the way, we have 2000, right? So in the worst case, you said it can be infinite, right? In the worst case, maybe stage two include like, because stage one took one already, so stage two may have, 1999 all the features, but it still may not satisfy. It means the selected, features are not good, or the samples are not good enough. Okay, so similar question from Nisar is, what if we cannot satisfy satisfy rate on this stage? So it means if we don't satisfy, okay, so the only thing we can do is add more features. Okay, normally adding more features at some point, like 10 more or 20 more. In that way, we can achieve that number normally, because this number, target number, 25%, it is not something like very difficult rate. Okay, so we can normally achieve it, but in the worst case, if we cannot achieve again, then we have more and more and more, and we have to use all of them, 1,999 reclassifiers. Still, if it still doesn't satisfy the rate, then we just fail the training. Okay, so let's consider stage one. In stage one, we couldn't satisfy the number. Okay, so we added all 2,000 features, 2,000 reclassifiers to stage one. So that is becoming, actually, if you you can imagine, this is actually same as the original concept of strong classifier. The strong classifier just from the AWS, right? Strong classifier means, summing all the selected reclassifier, 2,000. That is one strong classifier before cascade, right? So stage one is becoming that big, very huge, strong classifier, but it still cannot satisfy the rate. Then it is useless. So we cannot use this classifier. Okay, we fail. The training fails. Okay, in that case, we cannot use it, and we have to train again with more. For example, we can add more samples, or we can add more features. So we have to change some parameters and size of samples, and we have to try to train the system again. Make sense? Okay, let's go. Okay, so stage two is constructed. Okay, then we go to stage three, and we are repeating the same step. Okay, so from stage three, we also add more features, reclassifiers, and try to satisfy the target number. By the way, stage three has, less false positive rate. So stage two was 25%, and stage three will be 12.5%, half of the previous one. So in this way, we are decreasing false positive rate again and again and again. Okay, so that is construct. So it's the final until the final one. Okay. So in that sense, then when to stop? So we started with stage one, added stage two. Oh, stage two is done. We go to stage three. Stage three is done. Stage four done. 5, blah blah blah. Then we are repeating, right? It looks like kind of infinite loop. So when can we stop the staging, adding stage? Okay, So Lisa has another question. What about the time to compare with strong class? You mean the speed? Yeah, definitely, training time, if you are talking about training time, so it takes more time to do the cascade, right? It's a long process. That's why, the training of this cascade training is learning takes a long time. Sometimes it takes, some days, actually. But in terms of detection time, so cascade is much faster than strong classifier, right? Yeah. So once it is trained, learned, then in real time, when we apply this classifier for detection, the scanning of the windows to the picture, it is much faster than strong class, just original, just one strong classifier. As we have discussed already, so we'll discuss about that issue later as well. But as we have already discussed, in every stage, we are not processing all the samples, because they are filtered out in early stages. By the way, early stages, normally they have very high false positive rates. Normally the number of reclassifiers are very small. For example, like, stage 1 just has 1 reclassifier. Stage 2 has 3 reclassifiers. So among, 2,000, 1 or 3 or 5, it is very small number, right? The calculation is very fast. And they are filtered out in every stage. So in the later, heavier stage, bigger stage, they are slower than earlier one, but they don't process many windows because most of them are already filtered out in early stages. So in that way, cascade classification is much faster than original just one strong classifier. Okay, so Raul answered, my question. Sawan also answered, we can stop when specified first positive, say 1%. Okay, Raul suggested, 0% of false positive rate. Okay, Sawan suggested 1%. Okay, so both of you are correct. Okay, it doesn't need to be just one number, but anyways, we have to set one very small number, right? I think it can be a kind of in between 0.0 and 0.1, because ideally we hope 0%, right? Exactly 0%, but false positive rate, okay? But in reality, it's not possible, right? So because in reality we have some errors, right? So instead of 0.0, we can expect like 0.01 or 0.001. So by the way, normally in practice we are using a smaller number than 1%. So 1% is still a little bit higher than our expectation. When we apply this in real case, real face detection, then 1% still gives us some error, some error false positives. Okay, so normally number is less than 1%, but a little bit higher than 0%. So 0.01 or 0.001 kind of stuff. Okay, yeah. Anyways, so the final stage, at some point it can be like a stage 20 or stage 30. So if it has the final false positive rate, so we need to set the target false positive rate of the final stage in the beginning, so we can determine the number of stages in that way. Make sense? So you also can make some kind of formula for that, right? So it is decreasing half, 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 half. Okay, so that number for the final reclassifier, final stage, is regarded as a target false positive rate of the whole cascade. Okay, so in this way, every stage should have the target for, because all of them has the same detection rate, right? 99 or 99.5 kind of percent, right? So they're all the same. So it's not so much important. But every stage should have its own target false positive rate, and the whole cascade also should have its final target false positive rate, very small number, 0.001 kind of stuff. Okay. Is it clear now? Okay. So in this way, we can add more stages until we reach to the target number. Okay. So this is the whole process to construct the cascade. By the way, there is one issue, in kind of practical issue. Conceptually, it is good, but practical issue, at every stage, okay, when we are processing every stage, we said, we add reclassifiers to the stage, then one by one, okay, then we check the target numbers, detection rate 99%, false positive rate 50%, okay. By the way, we have actually two numbers, not just one, practically, even though we have the fixed number of 99%. Then how can we satisfy these two numbers at the same time? If there is just one number, we can just compare, oh, is it larger than this number or smaller than this number? Then it's okay. But when it is two, for example, sometimes the detection rate can be less. False positivity rate can be higher. But sometimes, if you add one more, the detection rate can increase. But false positive rate can decrease or increase, right? So they are different values, right? They can show different numbers. They can vary in different different direction. So it is practically difficult to satisfy, these two numbers at the same time. So do you have any idea, how to satisfy these two numbers at the same time? Okay, let me answer the question from someone. You asked, should we use all the 2000 features? No, we don't need to do that. Yeah. So if we reach to the target number, then, by the way, we selected 2000 features. That is kind of poor, okay? The maximum number of features and reclassifiers we can use, but we don't need to use all of them, okay? So if the cascaded structure, once it reached to the final target number, very small false positive rate with just all, together 1000 reclassifiers in the cascade, then that's it. So we just use 1000. Okay, so 2000 is just kind of, poor and prepared, with set of reclassifiers just for training. But in reality, the number of reclassifiers features may be smaller than 2000, or sometimes more than 2000. So it depends on the training set. Okay, so let's go back to this issue now. How to satisfy these two numbers at the same time? By adding. Okay, so what I mean is, I have one feature, one reclassify F40. If in the beginning, just with one feature, one reclassify, if it satisfies these two numbers, 99 and 50, then it's done. It's good, no problem. By the way, in case it doesn't satisfy, one of them may be wrong. For example, target rate is 98%. It is not 99 yet. But the false positive rate is 0.4. Then, false positive rate satisfies, but target detection rate is not satisfying, right? Then we have to add one more feature, right? So I added one more. By the way, at this time, the detection rate is 99%, but false positive rate increased, like 0.6. It doesn't stay, right? Because we added one more feature. So the results can vary, but they are not varying in the same direction. Okay, so then how can we make sure these two conditions satisfy at the same time? Anybody has any idea for that? Okay, yeah, so, change the window. Ordering the features by alpha might be best way. Yeah. Okay, so let's discuss together. Okay, so this is the solution. So in reality, because we cannot estimate, exactly, because the features are just features, right? So we cannot estimate exactly, they will keep the same level of detection rate, and the target false positive rate will decrease. Sometimes it can increase, sometimes it can be decreased, right? So in practice, it is almost impossible to satisfy both of them at the same time. Okay, so the solution, you may come up with better idea later, but the approach of this paper is two-step approach. So firstly, okay, so we cannot satisfy both numbers at the same time. So it is trying to satisfy the first one, the detection rate first. In the first step, just satisfy detection rate. So we are fixing the detection rate, 99, okay, 0.299. Okay? So how can we achieve this goal? So it means we are not allowing the detection rate is going down under 99%. Okay, so to achieve that goal, what we can do is we can adjust the threshold. Do you remember the thresholds? Okay, so let me go back to the previous slide. Okay, so this part in original, strong classifier, this threshold part was the half of all the sum of alpha. That was the default, threshold. Okay, but in this, case, we are modifying the concept of threshold. It can be adjusted. Okay, so in every stage, when we are trying to satisfy D and F numbers, okay, so now we are adjusting this threshold to satisfy number D first. Okay, so we can make it. How can we? Okay, so let me give you a question. When we have the target number is 0.99. By the way, the current with the given, the classifiers, the current D is 0.98. Okay, then to satisfy 0.99, how can you adjust the threshold? Do you want to make it lower or larger? Larger? So I think it should be in current, direction, it should be lower. So by lowering the threshold, it means we are allowing, so just based on this formula, okay, let me show you this one again, okay? So in this formula, okay, so when the sum of the alpha weighted reclassifier is larger than threshold, then it is phase, right? If we lower the threshold, it means the more windows, more samples will be determined as phase. It is increasing the number of phases, true results. It means we can increase the detection rate. So because we have to increase the detection rate now, right? From 0.98, we have to increase it until up to 0.99. So to increase the detection rate, then we have to decrease the threshold. Yes, it is depending on the current feature. Okay. 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 So let me show you another example. Okay. So this is a little bit in the beginning, a little bit tricky, concept to understand. So I prepared this slide. So here, sorry. Okay. So we have the samples here. So some positive and some negative. Okay. So for all these samples, we are trying to apply current stage, stage classifier, HX. Okay. So let's consider two different thresholds. Oh, no, not alpha. We are not. Alpha is already determined from the AWS. Okay. It's fixed number. We cannot adjust the alpha. Instead of alpha in the left side, we are adjusting the right side threshold, the whole threshold, instead of this number, half. Okay, so initially, this number was in this blue line threshold. This is initial default threshold. Okay, so let's say we have just 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say we have I didn't draw everything, but we have 10 samples. Okay, nine samples, for example. Okay, and using this threshold, default one, what is okay, so first of all, how many phase samples do you have now? Can you classify? 4. Yes, we have 4. How many non-phase samples, negative samples? We have 5. Yes, 4 and 5. Okay, yeah. And then we're using the default blue threshold value here. So what is the detection rate? Yeah, it is about around 75. It is exactly 75%. Why? Because there are 4 phases in this database, but just 3 of them were classified as phase, right? So 3 out of 4 is 75%. That is detection rate. Make sense? Okay. Then what is the false positive rate in this case? Yeah, 0%, right? There's no on the right side here. So it means, if on the right side, this is the true case, right? The result, the classifier. Okay. So now we are talking about one stage, okay? Every stage. So this stage classifier, when we apply all these samples, okay, then from this threshold, the right side, 1, 2, 3, all these faces, 3 faces will be yes. Okay? All other 6, no. Okay? So, in that case, the detection rate was 75% because one of the face is missed, right? Misclassified. And false positive, 0, because we have all just face. There is no non-face included in this, number 1 result. I mean, yes result. Okay, yeah. So the correct number we get from this classification, sample classification, is D equals 75%, F equals 0%. Okay. So first of all, in the first step, okay. So again, our target is to satisfy these 2 numbers. We are now, let's say we are now at stage 2. Then detection rate will be 99%. False positive rate, target false positive rate is 25%. Okay. So false positive rate already satisfied. Oh, good. 0% is much better. But detection rate is too small. It should be higher, right? It should go to 99%. So now, to satisfy these 2 numbers, we don't care about false positive rate for now. Okay, we just focus on detection rate in the first step. So to satisfy D, the current 175 is not good. So what we can do is we can lower the threshold. So move the blue line to this green one. Green one. Okay. Then what is the detection rate? It is becoming 100%. Okay. So because all the face samples can be determined as yes, 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 yes. Oh, they are all classified as faces. So detection rate is now satisfied. Okay. So this way, with some rates, okay, you can decrease the threshold. Okay. Then we can achieve at some point. Okay, we can stop at some point. We can achieve, the detection rate more than larger or equal to 99%, for example. Okay, that is first step. We have to stop there. So we stop at this green line threshold value, whatever it is. Okay, and then the next step, once we fix the detection rate in this way, and then we look at the false positive rate. It is now becoming 20%. Oh, it's a very good case. When I satisfy the detection rate, the false positive rate also satisfies, right? Less than 25%. It's a very good case. Then we can stop the classifier here. So the threshold of this reclassifier is set with as this, green line, because it is satisfying detection rate and false positive rate. But if, in other case, if it doesn't satisfy, or it satisfies the detection rate, right? But the false positive rate is still higher than 25, like 30% in case, right? Then what can we do? At that moment, we can determine, oh, this stage is not satisfying the target numbers. So we have to, yes, add another reclassifier. So this is actually the moment. So in our previous, kind of simplified explanation here, okay. So okay. So in this step, from number 2, 3, 4, 5, okay. At the step 4, we said, if D and F satisfy. Okay, so this is this kind of 2 steps, right? So once we adjust the threshold and satisfy D first, and actually what we are focusing on is F. Okay. So once D is set using thresholds, then we are looking at F. So finally, we check just F value, force positive rate, if it satisfies the target number. Then stop. If it doesn't satisfy the target number, then add more feature in this loop. Make sense? Okay. So to satisfy these two numbers, so we have two steps. Firstly, we adjust the threshold to satisfy D first. Once D is fixed, the threshold is determined to satisfy V, and then we check force positive rate if it is satisfied. Not satisfied, then we have to add more features. Satisfied, then we can stop there. Is it clear now? Any question? Yeah. So in the next slide, the same, kind of, example. So by lowering, the threshold, like from blue to green line, okay, then it is increasing the threshold, the detection rate. But if we move the green line to the yellow one, the left one, okay, yellow one here, okay, then we can increase the detection rate. Now, if there is nothing more than 100%, so it is 100%, right? So in this way, by decreasing the threshold, we can achieve higher detection rates, true positive rates, from 70% to 80%, 90%, 100%. So even we can achieve 100%. Okay. It means, what is the meaning of this? By the way, what is the meaning of this yellow line, yellow threshold? Yeah, higher force positive rate. More exactly saying, what it means. Okay, so this is 0. Okay, we use the threshold 0. Then the minimum value. Yeah, so all samples, or yes. So this classifier say everything fake. There is no negative answer. This is very becoming very optimistic guy. Okay, oh, your face, your face, your face. Everything is fake. So it is useless, right? So it is so it has too high 100% of false positive rate. Okay, so in this sense, sometimes we have to consider these two accuracy. When somebody asks you, oh, what is the performance accuracy of your face detection algorithm? If they ask you just the normally general people normally ask you detection rate, true positive rate. Oh, what is the detection rate of your detection algorithm? Then you can if you just focus on the detection rate, the true positive rate, you can make it 100% very easily. Okay, so in that sense, the question is wrong. You cannot just ask detection rate. The detection rate is also important because we have to detect faces, right? I don't want to miss any, misclassify any face as non-face. But the more important question is, what is the false positive rate? So by adjusting the threshold in this way, increasing the threshold, I'm decreasing the threshold, and we can achieve the detection rate, very high detection rate, very easily. But to satisfy the false positive rate is much more difficult. That's why we are building this kind of complicated, algorithm to satisfy both of them. Is that clear? So every time you are considering any classification system or detection system, so you have to show and you have to consider these two numbers. What is the detection rate? What is the false positive rate? Okay, just one of them is not meaningful enough. Is it clear? So, anyways, so based on this kind of concept, okay, this kind of practical, kind of concept, what we are doing is, to satisfy these two numbers at the same time, using, actually not at the same time, using two steps, right? Okay, and we can add more features if it doesn't satisfy. Okay. Okay, so I think you have one question. Okay, please, why b equals 75? The first test. Okay, so the first test, you mean the blue threshold, right? So this blue is assuming that this is just an example, okay? The blue is the initial default, default threshold from this formula. It was here at this position. Then it means if any value, the sum of alpha rated reclassifier, so we can apply all the samples, then we can calculate this number, right? The left side number. And then three of these samples, 1, 2, 3 phases were classified as number 1. Yes. Okay. Then by the way, there is one more actual phase sample here, a little bit darker image. So it was not classified as yes using this threshold. Okay, so 3 out of 4 phases are detected as phase. It means true positive rate is 75%. 3 over 4 multiply 100. Okay, it's becoming 75%. Is it clear now? Okay, yeah. So yeah, so that's what, okay, 75%, right? So if we decrease the number, the threshold to green, then 4 over 4, right? 4 out of 4 is becoming 100%. Okay. Okay. So I think that's all for today. So it's almost done. Okay. So from tomorrow we'll finish this step, with some practical issues. So let me explain. So the whole algorithm is working this way. So cascaded classification is much simpler than AWS algorithm. So in this way, we can construct a cascade structure, and finally, we can use this cascaded widget. So if you have seen the OpenCV face detector, so it has one XML file, okay, that includes this cascaded structure. So you can use it for face detection. Okay. Okay, so we'll finish this tab tomorrow and we'll move to the next topic tomorrow. Okay, thank you very much. And any final question? No? All good? Okay. Okay, yeah, so thank you very much. And I want to formally finish the class. And okay, question. So I think you have any question about the assignment? Thank you for others. And someone has a question with the assignment? Mm-hmm. Oh yes, scripting languages. So do you want to use any script languages? Oh yeah, you can use MATLAB. Yeah, so I mentioned MATLAB before, I think. Yeah, so MATLAB is kind of very popular, in computer vision, so it's okay. Python is okay. Okay, MATLAB, Python, they are kind of very popular. C, C++, Java, C Sharp, kind of more kind of general language. Okay, okay, good, good. Thank you. Thank you for asking. Okay, thank you very much. Have a nice day and see you tomorrow. Thank you. Bye.